Let's talk about the molecular orbital theory. The key points of molecular orbital theory are: molecular orbitals consist of atomic orbitals. Molecular orbitals are the linear combination of atomic orbitals. Valence electrons are considered to be shared by the whole molecule, and the numbers of molecular orbitals equals number of atomic orbitals. The theory deals with a single electron interacts with all the other electrons and nuclei in the molecule. The very basic difference between molecular orbital theory and valence bond theory is the valence electrons are localized or delocalized. Here shows an example. The electrons at pi orbital are localized in valence bond theory, while the molecular orbital theory supposes that the electrons at a pi orbital are delocalized, shared by the molecule. Even the molecule at the far end shares the electrons too. Though very less chance, the pi orbital spreads over the molecule. One method to construct a molecular orbital for a molecule is the linear combination of atomic orbitals. As depicted here, the addition of a wave function of s orbitals results in the bonding orbital and antibonding orbital. You see that two atomic orbitals form two molecular orbitals. The energy change in the combination are shown at the bottom. The formed bonding orbital has lower energy than the atomic energy, while the antibonding orbital has the energy higher than the atomic orbitals. You may understand this linear treatment on wave functions from the viewpoints of wave interference. Two waves with the same phase create constructive interference. The combination of the two waves will form an enhanced amplitude. So in molecular orbital theory, bonding occurs. On the contrary, the destructive interference of the two waves results in lower amplitude, or two waves remain in its state, no interference. Therefore, no bonding or antibonding in molecular orbital theory. Here is the energy level diagram, or say molecular orbital diagram for dioxygen. The contribution of each oxygen atom to the dioxygen molecule is guided with blue dashed lines. From the bottom up, two 1s orbitals form sigma 1s and sigma 1s star orbitals. Star denotes for antibonding orbital. 2s orbitals compose sigma 2s and sigma 2s star. One of p orbitals, say pz orbital in one oxygen, forms a sigma 2p orbital by bonding to the pz orbital in another oxygen. The two left p orbitals, px and py, forms pi 2p orbitals with the same orbitals from the other oxygen. Also, the antibonding orbitals, pi 2p star and sigma 2p star, are formed. The total number of electrons for dioxygen is 16. We can fill the orbitals with the electrons from the bottom up. The last two electrons have to be filled the two pi 2p star orbitals separately. Using molecular theory, we find there are two unpaired electrons in dioxygen. The experiments confirmed that oxygen is paramagnetic, which means unpaired electrons in oxygen. But chemical structure of oxygen from valence bond theory cannot be used to explain the paramagnetic property of oxygen. Now, using molecular orbital theory, the origin of paramagnetic properties of oxygen is clarified successfully. Bond order equals the number of electrons in bonding orbitals subtract the number of electrons in antibonding orbitals divided by 2. For example, bond order of dioxygen, 10 electrons in bonding orbitals, 2 electrons in antibonding orbital, divided by 2, then we have 2. The bond order of dioxygen is 2. We should know that if the bond order is greater than 0, then the molecule is stable. Otherwise, the molecule is not stable or will not exist at all if bond order is 0 or negative.